Recording is rolling. It is Monday, March 3rd. So here's the plan for this whole week. Now we're moving on to optics. So that's the green banners and the poster. All right. So you guys see the new posters hanging around the room. Got these green banners. You can see green, green, green. Right. Now today we're going to focus on reflection. You guys see this law of reflection here? Okay. And we're going to make some ray diagrams related to mirrors. So actually these right here. Here, I'll show you guys some bigger versions of those. Okay. So you're about to see law of reflection. And then, well, we'll look at some like fun house type mirrors, convex mirrors, concave mirrors. And we're going to make all these ray diagrams today. You guys have some copy paper in front of you. I'll have you guys do those and turn those in at the end of class. Well, I'll do them with you guys, so you'll know exactly what they look like. Okay. Tomorrow, I want to do refraction. Actually, tomorrow the next day. So we'll also do some ray diagrams, but I have a lab lined up for you guys with some prisms. So we'll be doing that called Snell's Law. Thursday, of course, you guys know is the SAT. So I've been posting the information about where that is on Google Classroom. Like here's one I just posted, SAT relocations. So I got two lists here. One is if you are testing where you are testing, which is most of you guys, because most of you guys are 11th grade, you're testing what room, it says exactly in this file. Now, guys, for those of you who are not testing, I bet your first few classes are going to be relocated. Do you know where you're relocated to? That answer is in this other file right here. Okay? All right, so you're either testing this one or you're probably relocated to your first few classes, so that's this one. All right? All right, so you guys got all that info right there. Okay, and then Friday, I wanted to do an activity with you guys to round out the week. Actually, I have a model right here. So this is called a Newton's wheel on this side and a Benham's wheel on this side. And yeah, okay, let's see how well this works. I think better in real life than on camera, but we'll get this working as well as we can. Guys, if you mix all the colors together, well, if I'm talking about paint, if you mix all the paints together, what color do you get? Brown. Yeah, kind of a muddy brown, right? Right. But what about a different kind of color mixing? If you zoom down microscopic on your phone screen, how many colors does your phone screen have? 3. And what are those 3 colors? Red, green, and blue. That's it. That's exactly it. Yeah. That's the only 3 colors on your phone screen. Now, if you turn on different ones, like if you turn on the red and the green, I think it looks like yellow to your eye, but it's really red and green, right? Okay. So if you turn on all the colors on your phone screen, which is the red, the green, and the blue at the same time, what color does that look like? White. White. Okay. You see that here with this this Newton's wheel. If I wind this up, you get the spinning. Watch what happens. Look, it turned white. You guys see it turned white? All right. So that will be we'll do that activity, maybe a couple of activities on Friday. Okay. Now I flip it over. Do you guys see there's only black and white on this side, right? Only black and white. Okay. Now this one might not work so well on camera, works better in real life, but if it gets spinning, yeah, I see it working well in front of my face, but not on camera so much, which is that you can create the illusion of color. So in front of my face, it looks like these are colors. It looks like a red band and a green band and a gold band. Okay. So on Friday, we'll round out the week with that. Okay, so you guys go to what we're doing? All right. So let's go back to top here, reflection. Let's start with some real basic reflection. I have a Paul Hewitt for you guys. Pull up Paul Hewitt.
Consider a candle. All optics books consider candles for objects, okay? Now we're going to look at the image that this candle gives in a mirror. Let's suppose right here, we have a mirror surface. Now what happens is light, let's just take from this point. Light goes in all directions. Some comes straight ahead, some comes up like this, some comes like this. The light hits the mirror in all directions. And when it hits the mirror, it, boom, reflects, yeah? And it reflects how? There's a normal. It reflects such that this angle, for example, here, will be equal to this angle here and reflect like that.
There, he just told you the law of reflection. That's it. Okay. Now, notice that the line that he's measuring with respect to is the normal line, which you guys know from last semester means perpendicular to the surface. So here's the mirrored surface, which is running vertical. And all these normal lines are running, well, perpendicular to those, and he's measuring the angles with respect to that. So here's the angle of incidence, here's the angle of reflection. hey guys, if this angle of incidence to this normal line is, oh, let's say 29 degrees, what is this angle of reflection? 29 degrees. That's it. Right? Now, you guys see how he has 5 light rays set up? 5 light rays, right? He's gonna use these to create the image, like the reflection.
And up here, this will reflect right back to where it came in. Because it hits flush, huh? Right angle. Huh? Up here, like that. And up here, like that. And down here, like that. Where this and this are the same. I don't have that drawn very well here. Like, if you like that. Get the idea? Now, you have your eye out here and you're looking. These rays here are all diverging. They're spreading out. See? They're spreading out this way, just as if they were this way. See? It's like discontinued, huh? But that spread out looks to you like that ray came from back here, that ray came from back here, that ray came from back here, that ray came from back here. It looks to you out here like there's a flame here and also a flame back here. And I could draw the same rays for the bottom of the candle. That's done in your book a little bit, yeah? Okay. And the bottom of the candle, it would look to you like it's over there. And so you would see the candle here, and you would see the image of the candle. And let me ask you a question. What's the distance here, and the distance here? Begin with SS. Same, gang. Same.
Same. Okay, so he just showed you a ray diagram for a flat plane mirror. We're gonna do some funhouse pictures. Oh, whoops, I meant to pull that up too. Here, let me find from my come on here. All right, here we go. Just gotta zoom in on this. All right. Hey, like this funhouse mirror type. Right? Why should you look all wonkety or big or small, right? Or how about if you look inside a spoon, right? Or if you flip the spoon over, maybe your reflection looks a little wonkety, right? Or how about a lot of modern day really powerful telescopes have actually used mirrors, but the mirrors are slightly curved. So what's the physics going on there? Like what does the reflection look like? So you guys have a paper in front of you, one of these copy papers. Okay. So put your name on your paper, name. I'll do a bunch of diagrams with you guys. And then at the end of class today, just turn this into the gray tray for credit. Title this Ray Diagrams dash reflection. Later this week, we'll do refraction with lenses. Right? Like if anybody's wearing glasses, those would be lenses, right? For refraction, right? We're not doing that today. We'll do that later this week. So today we're just focused on mirrors. Okay. Right. And we're going to do 3 examples on the front of the page and 3 on the back. So across the middle of the page, get a horizontal line going all the way across. I got a dashed line there. That'll represent, say, a floor. And then go about a quarter of the way up and do another dashed line. And then go about a quarter of the way down and do a dashed line. Right. So that's for 3 different examples. Okay. Now on this side of the page, well, here, let's do this one. The very first one. I'm going to create almost a plane mirror, but maybe has a little bit of curvature to it. It's a little bit convex. You guys see it? It's a little bit convex. Okay. Now the next 2, I'm going to have more significantly convex. So this one here, and then this one. Well, I go like right here, like this. Right. So I'll have my object always on the left side of these mirrors, and then we're going to see what happens to the reflection. Okay. But here, I'll even spell this out. Convex mirrors. Right. So a mirror would, of course, be for reflection. And then it could be convex because I'm going to put my object always on the left side of these. Right. Kind of like you're looking at the back side of the spoon. Right? Look, back side of the spoon. What does the image look like? Okay, guys, that. Now, I need to define how curved are these mirrors because I want to make them all a little bit different, just to get some different ideas across. Okay? And here's how I'm going to define how curved is the curvature of a mirror. Okay? Is a focal distance, like focal length. Okay? So it goes like this. Suppose you had a big spherical ball. You guys see this big spherical ball? Right? And you're like standing in front of it, and you're watching light rays bounce off, kind of like Paul Hewitt was doing. We're about to do also, right? Well, how do these light rays bounce off? Now, if there's a light ray headed straight towards the center, of course, it bounce straight back. But what if it was like comes in on some angle? So you guys see from the center. to this point where the light rays bouncing off, I have this normal line. It's kind of hard to see, but real faint. I have a normal line right here. You guys see a normal line going point right there? Yeah. Now I have like a red laser light. Maybe this is the incident ray right here. It's gonna bounce off, going somewhere that way. So this angle of incidence matches this angle of reflection. Is it? That okay? So that's the law of reflection. So law of reflection is just the same. But how do I know? Let's say these angles. Well, do you guys see like this laser light is aimed straight for this focal point, which is the midpoint between the center of the circle and the edge, right? And that corresponds to this reflected ray reflecting parallel to that radius. Or you can think of it the other way. If you have a ray coming in that's parallel to the radius, it's going to bounce off boing in such a way that the reflected ray aligns with this focal point, which is halfway between the center and the surface. You see that? Okay. So what I'm saying here, very simply, as an equation, is that the focal distance is half of the radial size. Okay, you guys got that? Okay. And I'm going to use that to define how curved is the mirror. Okay. Now, if the mirror was a plane mirror, look, guys, let's start with a flat plane mirror. If the mirror was a flat plane, what would the radius of curvature be? Hold on a minute. Guys, what if you mirrored the entire Earth? Mirror the entire Earth. Is the Earth so big that it's kind of hard to tell that it's even curved? Right? You might think that you're on a flat plane. Right? And that would be if the radius is very, very, very big. Oh, sorry, I'm gonna ask you guys. You guys would have said big, right? Very big. Right? Could it approach infinity? Infinity? Like, what if this ball was like the size of the observable universe? Right? You guys see that? That would definitely be hard to distinguish from truly flat. Right? So, if that's true, what's your focal distance for a plane mirror? What's infinity divided by 2? Still infinity, right? So what I'm trying to get at is, for this very first one, even though it's a little bit convex, let's sort of as best we can approximate a plane, right? Which means I'm going to put the focal point as far away as I can, which is going to be on the far right side of my paper. I'll put an F for focal point. Okay, you guys see that focal point? Okay, so not exactly a plane, but kind of close to a plane, right? Now the next one, I'll put the focal point closer in. Let's say it's more tightly curved. Okay. And the third one, I'll put it really close in. So it's a really, really tightly curved mirror. You see that? So my mirrors are getting successively more and more tightly curved. Right? Or that could sort of correspond to like the object changing its distance also from the mirror surface. Right? Let's get some objects on the board. Right. So get some object here. Now, Paul here was using candles. I like stick figures. Pick your favorite. You can put whatever object you want. Some textbooks use an upward arrow. I'm not really a fan of arrows because we're going to draw a bunch of rays, and I think it gets kind of confusing. But I think stick figures are good and candles are good. Second picture, let's put a stick figure right about here. Maybe third one, well, I don't know, maybe about the same spot. Okay. Okay, so all of these could be like looking at the backside of a spoon, with the very first example we're going to do being actually pretty close to a plane. Okay? Right. Everybody good? Everybody good? That's good. Right. Right. Now, Paul Hewitt was doing a ray diagram with 5 different rays. I can solve it with 2 rays. We're going to do all 6 of these examples with just 2 rays and figure out where is the reflection. Right. So you guys ready for this? So everybody's up to where I am so far, right? You guys got your name. You guys got ray diagram with reflection. You guys got 3 floors, 3 mirrors with their corresponding focal points, and 3 objects. Here, I'll label these object while you guys are catching up. Object, object, object. So this could be like a real world, there's something actually there, object. Right. Now, let's start from the top of this guy's head. Top of his head. Right. And let's have a ray of light going parallel to the ground. Right, parallel to the ground. Okay, you guys got that? Okay. Now, if this was a true flat mirror, wouldn't that light ray just bounce straight back? That'd be the case, right? Okay. Now, but this one has a little bit of convexity to it, right? A little bit of curvature. So it's going to bounce off, just like I showed you guys on this poster here. Okay. It's kind of like we just created this line right here, like parallel to the floor, this being the floor down here. We just made this one. I need to bounce this off so that it could extrapolate backwards through the focal point. You see that? We're about to do exactly that. So from this point, it's going to reflect. It's going to bounce a little bit up to the left. Okay, so not quite straight back. So do you guys see how I have my ruler aligned with the focal point? You see that? go ahead. That's good. The boing gonna bounce off that direction. Line that. Going that way. Okay. And then while I'm at it, I'm going to extrapolate backwards into the page and say, well, this looks like the light ray came from sort of that direction. Okay. Okay. Can you guys do that? Okay. Boing. So there's one light ray, it bounced off. Okay. And it could be going either way. You could have shown a laser light parallel to the ground across the top of his head and it bounces up to the left. Or you could have had a laser light coming up from the left a little bit and it bounces off the boing back parallel to the floor. It could go both ways. Okay. All right, now the next ray, let's go back to the top of his head. So that's the starting point for all these, top of this guy's head. The candle flame, if you have a candle. And let's aim the ruler straight at the focal point. So what if there was a ray of light headed straight for the focal point? To the top of his head. Now, of course, no light is actually crossing the mirrored surface. So if you want to keep going with it, I'm just going to dash this. Like, well, it looks like it's coming sort of from that direction. Right? Okay. Now that light ray is going to bounce off the boing back parallel to the floor. Back parallel to the floor. So see how I have my ruler parallel to the floor right there? Okay. A boing back that way. And then extrapolate back to the right, back behind the mirror. It looks like this light ray came from sort of this direction. Okay. Okay. So here, I'll recap everything I did so far. We're trying to catch up. So the first light ray I have across the top of his head parallel to the floor. That bounces a little bit up to the left so that you can extrapolate back to the right and it would go exactly through the focal point. That's how you know the direction of these things. Okay. Then I went back to the top of his head and made a line straight for the focal point. Of course, it dashes once it crosses the mirror because no light actually crosses the mirror. What the light actually does do is it reflects back parallel to the floor. And I furthermore extrapolated that one backwards behind the mirror. Like anything behind the mirror is dashed, okay? Because it looks like that's where the rays are coming from. Okay, everybody up to where I am now? Everybody good? Okay. Now, do you guys see where those rays cross behind the mirror? It's right there. Bam. Well, that is also the top of his head, because we started these both also at the top of his head, okay, for the reflection. So here's your image right here. Okay. And this is a virtual, I meant to call it upright. So upright virtual image. I see that? An upright virtual image. Okay. Upright because it's well, it's upright rather than upside down. Like later on, you might see some inverted images, but this one's upright. Okay. Virtual because it looks like it's on the opposite side of the mirror. That's as opposed to a real image, which we'll see later today. But for now, it's virtual. Okay, and it's an image because it's the reflection rather than the object itself. Is it? Okay. Oh, look at that. Remember, this convex mirror is pretty close to a plane mirror. And I know, say, when I'm brushing my teeth in the morning, if I'm standing 3 feet in front of the mirror, my reflection looks like it's 3 feet on the other side. Okay? This is pretty close to that. In fact, there's an equation that goes with that. And the equation is this right here. So here's a plane mirror. This is what Paul Hewitt did exactly, was this. Here's Paul Hewitt's example, basically. Okay? And here's the equation that will handle all these mirrors, all these mirror images. It goes like this. 1 over the focal distance is equal to 1 over distance object plus 1 over distance image. So let's check the math. Say, does the math align with this ray diagram? This would be the same story from a different point of view. Let's say from an algebra point of view. 1 over focal distance equals 1 over distance object plus 1 over distance image. Okay, you look at that? Okay. I can measure these with my ruler. So this focal length I have as, well, it's just really, really big. You guys see it's like 30-something centimeters. Okay. Actually, you know what? I want to fudge this one, this first one a little bit. Okay. Let's make believe that this is actually a true plane because it's pretty close to it. Okay. Guys, if it's truly a plane mirror, what's the focal distance equal to again? Infinity. Okay, so I'll do 1 over infinity. Okay. Now, if you call it convex rather than concave, there's actually a negative sign that goes there. But it doesn't matter. Either way, you guys should get the same answer from this. Okay. 1 over distance object. Now, if this object is sitting, about 3.5 centimeters from the plane, I'll do 1 over 3.5 centimeters. Okay, plus, and let's say I want to solve for where is the image, distance image. So I'm going to solve that algebraically, and we'll see how close is that aligned to the ray diagram. You guys got that? Okay. So who can tell me, guys, what is 1 over infinity? Huh? Straight up. What's 1 over a big number? 0.0000018. What if I make the number a little bigger? 0.0000018. What if I make the number a little bigger? What if I keep making the number? Guys, what is 1 over infinity? 0. This is 0. You guys got that? Okay. Here's another way to ask the same question. Suppose you buy a lottery ticket one day and you have a 1 in 20 million chance of winning. Isn't your chance of winning basically 0? Right? Even if you include the negative 0 is still 0. So 1 over 3.5 centimeters plus 1 over distance image. Okay. Now you can do a few more algebra steps, but you can probably see by symmetry what the answer is going to be. Guess what's the answer to this going to be? Negative 3.5. That's centimeters. You guys see that? Because that would those two fractions would zero out. Okay, you guys see that? Okay. Now look what we got. Usually how I see textbooks do this, I've always seen textbooks define the object as being on the positive side of the mirror. And in this case, the fact that the image comes out negative, hey, that's what corresponds to it being a virtual image. That's what virtual means. It means you have, well, it means this number's negative. Okay, like the image is on the opposite side of the mirror. Oh, and that's actually why I also tagged a negative sign to this focal distance, because I have the focal distance on the right side. Okay, you guys see that? And last thing, let me make my measurement, make sure this distance right here. Yep, that's 3.5 centimeters on the opposite side. That matches my math. So my picture and my math aligned. They both tell the same story. You guys see that? Right. Now, what if you took that fairly flat convex mirror and you make it more curved? And then later on, we'll make it even more curved. We're going to see what happens. So you guys see, definitely these last two, we're looking on the backside of a spoon for sure. Backside of the spoon. Right. So let's do the exact same process as we did for the first one and see what happens. So first ray, skirt across the top of his head, parallel to the floor. Now that ray is going to reflect which direction? Is it down to the left or up to the left? Up to the left. And how exactly? Oh, well, just align your ruler with the focal point. And boing, goes off that way. Or if the ray came from that direction, it would have boing back parallel to the ground. Which is kind of what we're about to do right here. Let's go back to the top of his head. Let's aim a ray straight at the focal point. Of course, it doesn't actually cross the plane, so maybe I'll just dash it the rest of the way. Okay, you guys got that? I should have dashed the first one too. Let me go back, redash this. Oops. Dash, 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 dash. I should have done that. Now, this ray right here is going to reflect which way? Yeah, parallel to the ground. Exactly. That's it. But parallel to the ground. Boing, right there. I'm going to also extrapolate back behind the mirror because it looks like that's the direction the ray came from. All right, you guys got those? Got all of that? So, while you guys catching up, here's a recap. We got one ray going across the top of his head parallel to the ground. That bounces off so that it aligns with the focal point. The next ray light, we're going to go back to the top of his head, aim straight for the focal point. And when that hits the mirrored surface, it's going to boing, bounce back parallel to the ground. Now, take all those lines and extrapolate them back behind the mirror. And do you guys see where those rays cross? Right here. Bam. That's the top of his head for the reflection. And his feet are on the ground, just like before. But we could do this whole process for his feet, but they would just end up being also on the floor. Okay? Kind of like Paul Hewitt's candle, same story. Okay. And there's your image right there. This is also an upright virtual image. It's going to label it image. All right. You guys good? All right. Actually, you know what? Since this one and the next one are pretty similar, so I'm just going to go ahead and move on to the third one, and then I'll do the math for it and what we're going to see. Because this is kind of even more extreme. What if you have an even more tightly curved spoon? And so you guys see that focal point is getting closer to the surface? The more tightly curved spoon. So same process. Let's go light ray across the top of his head parallel to the floor. Zip. All right. And that's going to bounce. All right, so put your ruler parallel, or align it with the focal point is what I meant to say. Okay. Extrapolate backwards, boing. Okay, you guys got all that? All right. Now, go back to the top of his head. Aim a light ray straight at the focal point. Zip. And when that hits the surface, extrapolate a little bit. When that hits the surface, it's gonna boing, bounce back parallel to the floor. And then before you move your ruler, remember to extrapolate that back behind the mirror because it looks like that's where that light ray came from. All right, very good. Again, actually, all three of these, especially these two that we're doing right here, are really sort of categorically the same or really similar to each other. Okay. Do you guys see where those light rays cross? Ooh, look at this little tiny image right here. Little tiny stick figure. Here's your image. You see image? Okay. Okay. So we started off with something that's pretty close to a plane mirror. Now we have a more and more tightly curved spoon progressively headed down the page. So let's do the math on this. Math time. So does the math tell the same story? We're about to find out. 1 over okay, so 1 over the focal length equals 1 over distance object plus 1 over distance image. Okay, that's my starting point. Okay. Now this focal length right here looks like maybe I'll call it 2.5 centimeters, I think. Pretty close to 2.5 centimeters. So 1 over 2.5 centimeters equals. Sorry, one more thing. It's negative. Oops. Negative. Right. See how the focal point is on the opposite side of the mirror? That also tells you that this mirror is convex rather than concave. So it's important that it's negative. Okay. My object is always going to be on the positive side. It looks like the left side is positive side. This looks pretty close to, it's about 5 centimeters. So 1 over 5 centimeters plus 1 over, okay, now I just got to solve for a distance image. You guys got that? Okay. Could you guys do the algebra and solve for that? So I'll do it. You guys do it. Let's see what we get. What's 1 over negative 2.5 minus 1 over 5? That's like negative 0.6, or you can do common denominator if you wanted to, if you want to leave it as fractions. Okay. Right. But that's 1 over di. Now, how do I get di? I have to do what to both sides? Take the reciprocal. Right? So you can do 1 over the answer, or there's actually a key for it right above the 7. I'll take the reciprocal for you. So I'm getting distance image is negative 1.67 centimeters. So we're between 1.5 and 2 centimeters on the opposite side. Negative means it's a virtual image, so the image should be showing up on the other side. That's been true so far today. Okay. Let's see. Go back to my ray diagram. How close is it? Because here's my image, right? So from the surface, is it pretty close to that? Oh, it's exactly there. Nailed it. So that distance right there, between 1.5, 2 centimeters, and the math said it should be between 1.5 and 2 centimeters. It's right there. Okay. You guys see how that worked? Right. We could have done the second one. Work out also about that. Right. So here's distance object on the second one. Right. It's about 4.5 centimeters. Here's distance image. Here, I'll just do this one real fast on my calculator. What's 1 over distance object is 4.5 plus 1 over distance image, which is 1 over negative. What is that? About 3-ish. Right. And then take the reciprocal. That should tell me where the focal distance is. It's negative. It says about negative 9 centimeters out. So, oh yeah. And my diagram showing about negative 8 centimeters. The math says negative 9. That's pretty close. I'm good with that. Okay. All right. Everybody get so far. Guys get so far. All right. Now we're gonna switch from convex mirrors to concave mirrors. I want to show you guys some examples of these. Let's start with here. I do have this in real life, but the well, let me show you guys the real life version. Okay. Here's the real life version of this, but it's kind of hard to get a very good angle for the camera for this. Well, you can kind of see it. You see there's an actual plastic pig down there. If I tilt this a little bit, you can see a little mirage looking right there. Right. And this works really well in real life. It looks like you could pick it up, but you can't because there's nothing really there. And what have we got inside? Oh, look, it's a couple of concave mirrors. Huh. Kind of like cosmetic mirrors have a little bit of concavity. Or if you went to the Hubble telescope a bit, there's a slightly concave mirror. Here, I'm going to pass this around. Pass this around. You guys go ahead. You can get a good look at it. You can take the mirrors apart. You can hold them up to your face if you want to see what does that do. But the video version here, I've got this guy muted, but he's just talking about it, saying, "Oh, look, that looks like a pig there, but it's not really there. It's not. Oh no, no, no." He pulls the mirrors apart, and all right, there's the actual plastic pig down at the bottom. Same thing. Right? So, we've got an image that looks like it's hovering in front of the mirror. Looks like it's hovering in front. Some people call it a hologram, but that's actually technically a different thing. It's called a real image. That's what it's called. It's called a real image. So what's going on there? And another example of concave mirrors. Now, I know that's a light example. Here's a sound example. Do you guys know what those are right there? Those are acoustic mirrors. Acoustic mirrors. They're also called whispering dishes. Sometimes you see this like out in a park somewhere like here. I know if you go to the University of Florida up in Gainesville, if you go to the physics building, in the lobby, they have a pair of these, or at least they did some years back. So how these work is there's some focal point. Maybe it's pretty close to where my arrow, you guys see my cursor? Right, maybe there's a focal point pretty close there. And on the other side, this one, there's a focal point. Now, these two dishes are aimed at each other. Suppose you and a friend walk out to the park, and your friend stands over here, and you stand right here, and you whisper something. Your friend can hear you as if you're speaking right in their ear, even though you're across the field. Now, you step over like 10 feet this way, you can't hear them at all. But if you're at the focal point and your friend's at the other focal point, you can hear each other. You can whisper back and forth and hear each other. Another fun example of that is, what is it called? A whispering chamber. Or so you guys know a lot of legislative buildings have those domes on them, like Capitol buildings and stuff, right? So there are lots of examples of these where inadvertently these whispering chambers were created. I don't think on purpose, but there are stories of these legislators like finding some point in the room where they can listen in, they can spy in on their fellow legislators, like on the opposite side of the room. Right? They have no idea that they can hear them because it's like, oh, don't worry, they're out of earshot. But think again, you're in an acoustic chamber. That may not be the case. Okay? So let's do the mirror version of that. Again, you guys notice that the mirrors we've done so far are all convex. That's the opposite. Let's flip over. Let's do concave. What if you flip the spoon over? So let's do some concave mirrors. Did I label the other ones convex? I did. All right, so I got convex is the three we did so far. Okay. Now these concave mirrors, I think, are going to be a little bit more exciting. We'll do 3 of these also, because these are all going to be categorically different than each other. Like those 3 convex, it's like, okay, well, kind of similar solutions. I see virtual images, blah, blah, blah. But that's not going to be true for concave. Concave depends, like, where's your eyeball relative to the mirrored surface? Right. So you guys got 3 floors set up. Floor, dash off some floors here. Right, you guys got 3 floors set up. Right. So I need some concave mirrors. Let me find my notes, exactly how I made these. Okay. So get a mirror right here, a little bit of concavity. Same thing here, a little bit of concavity. Yeah, see about the same thing in all of these. Okay. No, I'll define the amount of concavity with the focal point, of course, as I go forward. I'm going to put the first one pretty close in. Here's my first focal point. The second one, maybe kind of medium. And the third one, I'm going to put like way back here. Okay. So I think the first one is really tightly curved. And the second one's not as curved. And the third one is getting relatively flat. Or another interpretation is after I put the objects on here, it can be kind of like you're holding the spoon really far away from your face. And then closer. And then you hold the spoon really close to your face. Okay? Because here, let's get some, are you guys ready for objects? Okay. For this very first one, there's a specific location I want you to put this first object. You guys see this distance right here? However far that is? Double that distance. Can you guys double that distance? And then go out a little bit further than that. And that's where the object is going to go. So here's your object. Let me say that all again. Okay, so for yours to look like mine, take this focal distance right here, double that distance, and then go a little bit further out. In fact, if you want to do triple distance, that could be great. The next one, let's put the object right on top of the focal point. And the third one, let's put the object pretty close to the mirror, like well inside the focal point. Right? Or as you guys are passing around those parabolic mirrors, if you pop them apart, right? Again, this could be if you have the mirror very far away from your face. And then the third one is if you have it very close to your face, kind of like the cosmetic mirror. Actually, I do have a cosmetic mirror here. Now, I don't know why this isn't working so well on the camera, but this side actually is flat. It is actually flat, so I get regular reflections. But if I flip this over, it has a little bit of concavity to it. Now, again, I don't know exactly why it's not working so well on camera, but if you try this in real life, I mean, the point of a cosmetic mirror is that it blows up your face. So let's see, is that the same story that the ray diagrams are going to tell? Let's see. So we'll start with this one here, where say the spoon in the mirror is very far away from your face. What happens? Okay. Now we're going to do the same rules we've been doing all along. So let's start with one ray that goes across the top of his head, parallel to the floor. Okay. Right, everybody got that first ray? Okay. Now that's going to reflect, guess which way that ray reflects? Ba-boing, right through the focal point. You guys got ba-boing, right through the focal point. Okay. Now, let's have another ray going, okay, from the top of his head again, straight towards the focal point. In fact, this ray is going to go through the focal point all the way to the surface, and then it's going to reflect which way? How about back parallel to the ground again? Zip, parallel to the ground. Is that true? Right. Now look where those two rays cross. Guess which point that represents? That's where the what is? The image. So put the top of his head where the two rays cross, and his feet are still going to be on the floor, which means that he's upside down. Look at that. Upside down. Okay. Now this is called an inverted because he's upside down, real as opposed to virtual image. Okay. You guys remember here, if I flip back a few minutes ago, all these convex mirrors were all upright virtual, right? Okay, they're all upright virtual here. But when you get to concave, that's not necessarily the case. You guys can try this too. Take a spoon tonight or take those parabolic mirrors that are being passed around class right now and hold it really far away from your face. And I bet you look like you're upside down. You guys think so? Bet you're upside down. Hey, you guys got that? Oh, here, I'm going to skip this one and come back to it later. All right. What if you hold that mirror really close to your face, though? Make it like a cosmetic mirror. What's going to happen? Well, let's see. Actually, whoa. Before move on too fast, I want to do some math. Let's do the math on this inverted real image. You guys remember I've been saying 1 over the focal length is 1 over distance object plus 1 over distance image. Okay, let's try it for this one. So this one, I have a focal distance that's it's about positive 2.5. So 2.5 centimeters. And the fact that it's positive tells me that it's concave. 1 over distance object. Now the object I've got as about 7 centimeters out. I'm going to solve for what is distance image algebraically. Can you guys solve that algebraically? You guys solve it, I'll solve it. Let's see if we get the same thing. 1 over 2.5 minus 1 over 7. Then take the reciprocal. I'm getting distance image is about 3.9 centimeters. You guys get about that? With that? Right. Right. The fact that it's positive tells me it's a real image, right? Positive means real image because it's on the image is on the same side of the mirror as the object. Looks like it's hovering in front. Now, is it about 4 centimeters out? Let's see. Oh yeah, it sure is. Look at this distance right here. It's 4 centimeters. 4 centimeters. Exactly what the math says it should be. Right? All right. Okay. Now you guys ready for the next one? All right. Now let's move on to what if you put your eye really close to that cosmetic mirror? Now what's going to happen? So let's go. Here's a ray going parallel to the floor, skirting right across the top of his head. That's always been the first one we've been doing, right? Now that's going to reflect off that mirrored surface and bounce which way? Straight through the focal point. Boing. Now, before you move your ruler, go ahead and extrapolate backwards behind the mirror. Because you're gonna say, well, it looks like that ray came from that direction. Even though, of course, no light actually crosses through the mirror. But if it did, it looks like it came out. Okay, very good, very good. Okay. Now let's go from the focal point right across the top of his head. Zip. Take it to the mirrored surface. And now that ray is going to reflect which way? Back, parallel to the floor. Zip. Okay. And before you move your ruler, go ahead and extrapolate backwards behind the mirror again. Like that. And look where those two cross. You guys see where those two cross? Okay. There's the location of your image right there. Okay. Now, guys, is this upright or inverted? Upright. Oh, I forgot to label object for these. Object. Oops. Okay, do that real fast. Okay. Yeah. Okay, so this is an upright. Is this virtual or real? Virtual, because it's behind the mirror. And of course, it's an image. That's an upright virtual image, just like it was for all the convex situations. This concave one is. Okay. Oh, but look at that. Guys, what's bigger? The object or the image? This is the first one where the image is bigger. Like if you look at all the examples we've done so far, this is the first one where the image is larger than the object. Hey, I think that's the purpose of a cosmetic mirror. Right? It's to blow up your face. There it is. Your face is blown up. Let's do the math on that. So 1 over focal is 1 over distance object plus 1 over distance image. Okay. So 1 over, now my focal distance I've got as looks like about 10 centimeters. Guess that's pretty close to 10 centimeters right there. Right. So 10 centimeters equals 1 over. Now, where's my object sitting? Looks like about 2 centimeters out. You guys see 2 centimeters right there? So 2 centimeters plus 1 over distance image, which I'm solving for. Right? Can you guys solve that equation? You guys do know where I'm getting all these numbers from, right? Okay, let me point it out one more time in case you missed it. Right. So focal length is from the surface of the mirror to the focal point. I measured that as 10 centimeters. Distance object is from the surface to the object. I got as 2 centimeters. Now these are both positive because they're both on the same side, which is in front of the mirror. Distance object is always positive. A positive focal length means it's concave. So we have, can I solve for distance image? I hope this shows up as a negative number. I hope, is the reflections on the opposite side. So it's 1 over 10 minus 1 over 2. And then take the reciprocal. I'm getting distance image is net. Oh, it's negative, just like it should have been. 2.5 centimeters. Right. Right. You guys good with that? Okay. And is that what the story tells? Well, from here to here. Yeah, that's pretty close. Yeah, on my picture, it's pretty close to that. Pretty close. Okay. All right, guys good? All right. We got one more diagram left. All right, you guys ready for your last diagram? All right, so this one, what if, okay, and here's the story, is what if you don't have the cosmetic mirror far from your face or close to your face? Or same thing with the spoon. You don't have the spoon far from your face or close to your face. You adjust this so that your eyeball is right on top of the focal point. What are you gonna see in that mirrored surface? Well, let's see what the ray diagram says. Right? So run a ray parallel to the floor across the top of his head. That's gonna bounce boing through the focal point. Okay. And then we'll go back to the top of his head and we're gonna run that through the focal point. And normally we take this all the way to the surface of the mirror, except now, that doesn't really work. So it kind of falls apart. Guess what the answer to this one is? No image. No image. There's no image. Right? And you could try that too. If you're passing those parabolic mirrors around, right? You can take them apart. You can put the mirror far from your face, close to your face, and somewhere in the middle, there's a lot of light, but it doesn't really create a coherent image. Now, what does that look like in the math? Say if you do 1 over focal equals 1 over DO plus 1 over DI. Okay. What if, do you guys see the focal point and the object are on the exact same location? So what if I do something like this, like 1 over 7 equals 1 over 7 plus 1 over DI? Okay. Guys, what is 1 over 7 minus 1 over 7? 0. And if you did solve for DI, what's probably the best thing you could get? Like infinity, right? Because 1 over infinity, we're back to that again. Is that, yeah, so there's no image there, no image. Right, you guys good with those? You guys good? All right, 8 questions so far. All right, so give you guys a recap what you guys have seen today. Right. We started with law of reflection. Okay. So law of reflection, if you have a reflective surface, a mirrored surface, and then from that you draw a normal line to measure angles with respect to. Right. This angle of incidence will always match this angle of reflection. Right. Boom, law of reflection. Okay. That's true for flat mirrors. That's true for funhouse mirrors, curved mirrors. Right. This has been true all day today. Okay. Now Paul Hewitt did a ray diagram for just a flat mirror. You guys saw that? Okay. Then we said, well, what if you do have a curved mirror? Now this would be a convex mirror, right? And we were able to define the focal point. Now, if you have a concave mirror, it's just this flipped, right? So you could put the focal point, say, on the other side for concave, right? But in this context, it's half of the radial size for curve. Okay. We did these convex mirrors. So here's convex mirror, here's a plane mirror. Okay. And we've been applying this formula all day today. So 1 over focal length is 1 over distance object, 1 over distance image. Distance object is always defined to be positive. Distance image, whether it's positive or negative, tells you whether it's a real or a virtual image. And the focal length, whether it's positive or negative, tells you whether you're dealing with a wait, make sure I get this right. What did you say? Oh, now I mixed up at right at the end of class, right? Okay. Concave would be positive and convex would be negative for the focal length. Okay. Okay. And then yeah, okay, then we did some concave mirrors, right? And that same formula still applies. We got that, right? Here's a cosmetic mirror here, but if you back your face up too far away, then you flip upside down. Okay. All right, so let's recap. So guys, double check your page. Make sure you got all 6 ray diagrams. Make sure you got your name, and this is for reflection. We'll do some ray diagrams later this week. This is for refractive lenses, but today's reflection mirrors. Make sure your name's on it. Turn this into the gray tray, and I will give you guys points for those. All right, and that is a wrap on today.